Now, this lesson 10, we are going to prove principal ideal. So, ring of integer is a principal ideal ring. Principal ideal ring. See, if in the proof, you take a z under additions and multiplications. Take a z under addition multiplications. Obviously, z is a commutative with the unity without a zero divisor. So, take a z as a commutative as a unity without a zero divisor. Z will be a principal ideal ring if every ideal in Z is a principal ideal. Because in the previous session I told, so every ideal is a principal ideal, but converse is not true. Every principal ideal may not be a ideal. So we are taking every ideal is in Z is a principal ideal. Let S be an ideal of a ring of integer. If S is a null ideal, S is a null ideal. But suppose if we take S equal to 0 for so that S a principal ideal. Let us suppose that S is not a 0. S is not a 0. So suddenly S contain at least one of the non-zero integers, say A. S contain at least one of the non-zero integer A. Since S is a subgroup of R under additions, therefore A belongs to S minus A belongs to S. Suddenly A plus of minus A belongs to S. Suddenly 0 belongs to S. So in this case, so I'm avoiding that case. 0 does not belong. I'm avoiding non-zero as a non-zero element of S. So in this case, this shows that S contain at least one positive integer. If A not equal to 0, then one of the minus A must be a positive. Choosing that. So yeah, we are principal ideal is an ideal. So we are S itself is a zero form. So avoid that is S should not be a zero form. It should not be a generator 0, because if you multiply in the generator of 0, if you multiply with what, we get a null. So avoid that. So if you choose an element A not equal to 0, A belongs to S minus A is also belongs to S. So that this shows that S contain at least one a positive integer, then one of the minus A must be positive. So this we can collection that. So take S is a plus, means only a positive set of all only positive integer in S. Choose that. I denote that is S plus. We are the set of all a positive integer in S. Since S certainly S plus is non-empty. Therefore, well-ordered principle S plus. So well-ordered principle is a less than property. So any element certainly less than that element. If we are choosing element certainly less than that element. S plus most possesses a least positive integer. Let S be a least element. We shall show that S is a principal ideal generated by S. S is a principal ideal generated by an element S. So that is S equal to generator of S. Suppose this is one way is correct, because you are avoiding non-zero, non-empty. You are collecting only set up all a positive integer. So we choose an element S is an element of S that belongs to S. That is the generator. S equal to set of all S is a generator. Now suppose that N is any integer in S. N is any integer in S. By the division algorithm, there exists integer Q and R such that N can be written as QS plus R. N can be written as QS plus R. Here Q and R is a quotient and a remainder. Suddenly, if R less than or equal to 0, less than S is a remainder. Suddenly R less than or equal to 0, less than S. So now S belongs to S. S belongs to S. Q belongs to Z. Q belongs to Z. Suddenly, QS belongs to S. QS belongs to S. Now, N belongs to S. N belongs to S. The difference QS belongs to S. The difference N minus QS belongs to a set, because now in the differences A belongs to S, B belongs to S, minus B belongs to S. Suddenly A minus B belongs to S, right? So that N belongs to S, QS belongs to S. So the difference N minus QS, that is belongs to S. This implies R suddenly in S, But the remainder 0 less than or equal to R less than S. But the remainder is here 0 less than or equal to R less than S. But S is the least positive integer such that S belongs to S. S belongs to S. N's all must be a 0. N's R must be a 0. So then N belongs to S. Suddenly N equal to QS. N is equal to QS. So what means that R is 0? R is 0. Less than or equal to R is 0. Less than or equal to S. Less than or equal to S. So either R is 0 or less than S. Suddenly, if assume R equal remainder is 0, suddenly you can write N is equal to QS. Where Q is an integer. Q belongs to Z. Hence, S is a principal ideal of Z. You are observe here. So Q in multiple of S. Q is a multiple of S. S is a multiple of Q. Hence, S is a principal ideal of Z generated by S here. So S is a principal ideal of Z generated by an element S. Since S was an arbitrary ideal in the ring of integer, therefore the ring of integer is a principal ideal ring. See, in this theorems, so we are avoiding a 0. So the avoiding a 0. So avoiding 0 is obvious case. So without a 0 divisor. So ring with unity and without a 0 divisor, Z will be a principal ideal if every ideal in a Z, because the principal ideal definitions is you are recalling. Let S be any ideal of any ring of integer. S is a null ideal, then S equal to 0, then S is a principal ideal. So let us suppose that S is not equal to 0. Now S contains at least one of the non-zero elements, say A. Since S is a subgroup of R under addition, therefore A belongs to S minus A belongs to S. A plus of minus A, suddenly A minus A 0, suddenly this S contains at least positive. So however, one case if a 0 is obvious, if a 0 belongs to S is an obvious, 0 is a divide, 0 is a multiply, there is nothing else. So you are avoiding non-zero. A not equal to 0 is 1 is minus A must be a positive. Then 1 of A and minus A must be a positive. 1 of A or minus A is positive. So now that type of element we are correcting. S plus be a set of all a positive integer S. So S is a non-empty, at least a single element. Then N can be written as by division algorithm, N can be written as QS plus R. So R is a remainder, 0 less than equal to R less than S. S is an element of S. Q is an integer. Integer and element of S. Its a product belongs to S. So by using a division algorithm, again with so S is a principal ideal of Z generated by S. Since S was an arbitrary ideal in a ring of integer. Therefore, ring of integer is a principal ideal ring. This is true. We already know the definition of principal ideal. By using the definition of ideals, principal ideal, we can prove this integer ring of integer is a principal ideal ring. By using the same statement, we extend this theorem. Every field is a principal ideal ring. extend this theorem, we write every field is a principal ideal ring. So what is the principal ideal ring? So by proof, you say you using the same proof. A is field as no proper ideal. What mean a proper ideal? Only a trivial ideal required, trivial or improper ideal. So A field as no proper ideal. So no proper ideal means A must be a improper and trivial ideal. What is a trivial ideal? Zero and itself. Zero and itself. The only ideal of the field are one null ideal. Some may say zero and itself. Null ideal, which is a principal ideal generated by zero. And second one, the field itself, which is also principal ideal generated by 1. Thus, field itself is always a principal ideal ring. Principal ideal ring. This is a theorem regard principal ideal ring and every field is a principal ideal ring. So we regard that regarding the ideals and the principal ideal. The principal ideal is few. Few means multiplying that element we get a whole element. Certainly is a sub ring form. So principal ideal. But every ideal is a principal ideal. But principal ideal may not be a ideal. This is the one. So in this using that, every field is a principal ideal ring. So every field is in the principal ideal ring. We are collecting only improper ideals or trivial ideals. Trivial ideal 0 and itself is a form. So 0 and it. So we are using that itself field itself is always a principal ideal ring.